So this video will help you equip yourself with the absolute foundational knowledge about what machine learning is and how you can use machine learning within your organization or existing application that you guys are working on. It's hard to keep up with the LLM revolution. It's hard to keep up with so many products every single week. So this video will help you equip yourself with the absolute foundational knowledge about what machine learning is and how you can use machine learning within your organization or existing application that you guys are working on. So let's get started with the video. So before we jump into the actual machine learning stuff, it's kind of important to understand the broader concepts like what artificial intelligence is and where does machine learning actually lie within the whole landscape of artificial intelligence. So, artificial intelligence or AI is just the science of making things smart and can be defined as human intelligence exhibited by machines. So, that's a very, again, like I said, it's a very broad term. And we can obviously declutter a lot of stuff into it. So, currently, speaking of today, where we are in the world today, so the systems implemented today are a form of narrow AI. So, what narrow AI means, like you pick up a particular use case and you build an application upon it. It can be something like that predicts the value of a particular wholesale item. It can be something that recognizes if a rider is wearing a helmet within the streets or not. It can be an absolute micro level use case that you can just pick and build stuff upon it. So even in the world today, the chat GPTs are again a micro application of a very broader term of the AI itself. So again, as depicted here within the slides as well, a system that can just do one or few defined things as well or better than the humans. Obviously, ChatGPT is doing a great job, but again, all of these narrow AI applications have certain limitations. Certain limitations that eventually humans would actually have to work harder to sort of evolve them. For example, ChatGPT hallucinating is like a huge example in itself. So, some of the common use cases, I believe you guys are already very well accustomed with this. So, object recognition, speech recognition, sound detection. So, we already have a lot of such micro level applications within the market, and prediction, translation, restoration. All right, so machine learning. And it states that it's an approach to achieve artificial intelligence through systems that can learn from experience to find patterns in a set of data. Now, there are two very important terms and probably a very important verb in this particular statement. So, you have a set of data, number one. You have to find patterns in that set of data. And that is crucial when you talk about machine learning. So you should have a ample amount of data set in case you want to predict something, in case you want to classify something, in case you want to transform something. Either the case, you need data. That's the step one. And obviously, with data comes a lot of refinement tasks. You have to run a lot of refinements within your data. You have to reconstruct your data, maybe transform your data a bit. So, finding patterns within the data, unless a model or a machine learning application cannot find these patterns, you cannot go ahead with it. So, a lot of people within the community would say like machine learning applications is 80% or 75% data and 25% or 20% actual implementation of machine learning algorithms. So yeah, that's just a gist of it. So ML involves techniques and teaching a computer to recognize patterns. in our case, obviously, we'll be training models and we'll be building upon those models. So helping models to recognize those patterns and to move ahead with actually implementing the actual use case is the core here. So moving along, learning by example, ML is all about predicting stuff essentially. And the stuff that we just discussed about the data and finding pattern is just listed here in a more verbose way. So it takes some data, learn patterns, classifies news data it has not seen before. So that's also something that we'll be talking about just in a bit. The beauty of ML is that it learns by itself from the data passed to it. So yeah. So what happens is like, it's just like you have been given a few dots. Just imagine you have been given a few dots that's been scattered across a two-dimensional space or a graph, and you just have to draw a straight line. But your teacher or your instructor asks you to actually make sure that your line passes through most of the dots. So this is what ML is about, is to finding that pattern, finding that sweet spot where most of your data would be covered or catered in a more specific way. So here we have two different ways of doing things that we have been doing lately, which are like explicit rules. If, for example, if I give you a use case that, hey, here are a bunch of emails and you can check the header of the emails, you can check the headings of the emails, you can check the description of the email, and just tell me whether this particular email is spam or not spam. So what would you do? You would actually go ahead and write a switch statement or a series of if and else statements to check if there's anything fishy within the header, if there's anything fishy within the title or description or whatever. So that is a more conventional way of programming that we have been accustomed to. The machine learning programs are different because first you need the data, you need to refine the data, then you need to make sure your models or your program runs over that data, learns the aspects and patterns of that data, and then try to do an operation. And while doing that operation, you have to make sure that the error values that your model gets are minimized. So your model has to be constantly readjusting itself. So that's what it is about. Reminds me of that step, the robotic step. Weird. Okay, deep learning. So we're not going to go into a lot of detail about deep learning because this specific video is just about machine learning. Probably we'll be covering deep learning in one of these technology one-on-one series a bit later. So now we started with artificial intelligence, and then we jumped on to machine learning. And the definition of machine learning is a way of applying artificial intelligence. Now, the definition of deep learning is a technique for implementing machine learning. So you can see where we're going with this. So machine learning is a huge subset of the AI itself, and deep learning is, again, a specialized use case of machine learning itself. So as you can see, we have a timeline here. The term artificial intelligence was first coined in 1950s. Machine learning probably began a bit formally in late 90s, but it was coined around 1980s. And 2010, which is not that far away, but yes, like 2010, it's just like around the corner. So the deep learning application started to pop up by then, so it's kind of interesting. All right, let's jump into some of the ML stuff, interesting stuff. So the problem is how to choose data to train ML systems, since we actually just drop this definition in itself that an ML program basically needs data first, and those data needs a few refinements. So we're going to talk about how can we get the data, what are the aspects that we need to look into the data, how should we retransform the data, and how this data has repercussions or implications on a machine learning model. So let's talk a bit more about it. So firstly, whenever we talk about data, for example, in this particular example, I want to build a model that sort of classifies between apple and oranges. So how do I determine that? The very first thing is that, okay, apple are red, or apple are more uh, you know, they have less textures than the oranges. um, we can talk about number of seeds, we can talk about the weight, and this is exactly that is being depicted over here. So what we call a certain attribute of a particular entity, in this case an orange, we call them features. So features are basically used to tell your ML model about the specifications or the capabilities of a particular entity. So in our case, we have the color of an orange is orange, the weight of the orange is 340 grams. So these are called features. Now, these terms that I'm going to use throughout the video um, are kind of important to the vocabulary of machine learning. So make sure you wrap your heads around it. So let's say we take a few readings and we have these uh, two dimensions. Consider it a graph, a two-dimensional space. I'm going to take you back to what, 8th standard. So we have weight on the y-axis and we have color on the x-axis. So now since we have these two attributes, weight and color, so I'm just gonna throw all my data points here. And as you can see, we have the couple of oranges over here and we have apples over here. But some guy actually turns up and tells you that, hey, apples are also green, so you need to accommodate those data points as well. So I say, okay, fine. So I throw in all shade of apples. So here we have certain sort of a visualization that we can start with. So here we have two features, which would mean two dimensions. So there's again another term. There's one term, features, attributes, dimensions. These three things are commonly used within the machine learning landscape, but what you need to know is that all of these three things are the same basically. Dimension is more like a formal term that is used because whenever we say throw in another feature or throw in another dimension within your data, it just means add one more column or add one more feature with respect to your entity. So in the plot on the right, the ML system can learn to split the data up with a line to separate the apple and oranges. So this can now be used to make future classification when we plot new points to the system. So let's say you have, once I've built this system and I know that this particular yellow line is the actual segregation and everything above it is obviously going to be orange, everything below it is going to be apples. So once you know this particular line, you know how to classify between both of these. So if you have like one data point and you throw that data point in and it lies somewhere here, then you know that it's orange for sure. So now another important term is choosing useful input features and how they sort of impact your ML models. So let's say instead of these 2 points of a particular orange, we begin with ripeness and number of seeds. Obviously, they all vary. They all vary in terms of different fruits. So obviously, they're not a very good measure. But since this data was provided to us and we sort of chose, or your intern sort of chose to, throw in ripeness on the y-axis, number of seeds on the x-axis, and he went onwards with sort of, trying to find a pattern. But just look at this mess here. Can you find a pattern here? By all means, no, definitely no. There's no line on this planet that's going to fit in here and that is going to show you that segregation. So that is when we say that our input features are not compatible with the model or they don't offer much inclination to the model itself, because you just cannot build a pattern out of it. And when you cannot build a pattern out of it, you cannot determine the segregations. So it's very important that we refine our data, that we drop certain features, certain columns, slash attributes, slash dimensions, slash features from our data to make sure that we only have a very lean amount of data that offers enough information to a particular ML model so that it can sort of create some sort of segregation. All right, let's spice things up a bit. We've been talking about 2 dimensions, x-axis, y-axis, boring stuff. Let's make it a bit interesting and let's add in one more dimension. And that's where people get crazy. But don't, if you're watching the video, don't leave now. This is the most fun part, because I'm gonna talk about cats and dogs now. So let's say we have 3 dimensions now. Your boss or your manager comes to you and he tells you that, hey, I need a program, or I need an ML application that if I provide a picture of my pet dog and a pet cat of my neighbors, so it can sort of differentiate between both and tell me which one is what, which one is the cat, which one is the dog. And he gives you like 4 or 5 features or dimensions. And so you're sitting at home at night sort of figuring out that, okay, how can I pull this off? So let's say you start with 3 features. And the very first feature that you sort of start with is, let's say the very first feature over here is number of whiskers. So yeah, those whiskers. And the second feature over here is, let's say, about number of patterns of a body of the entity, in our case, cats and dogs. So we're taking number of whiskers, we're taking number of spots or patterns on the body, and third one is the funny one. Let's say we take the size of the nose. Width of the nose, size of the nose wouldn't be a very good feature. So in our case, and let's say another feature is length of tail, height, and stuff like that. So obviously in that case you would be plotting it somewhere. So here, whenever we're working in a 3-dimensional space, so obviously we cannot create much segregations in terms of lines. Obviously your perspective now changes. So instead of a straight line like we had here, in 3 dimensions you have to consider a plane. So this particular plane here, so the cats are visible to you because they're like above the plane, and the dogs are like faded out because they're like below the plane. So it's like you have, so let's say this is the plane, and the cats are basically above here and the dogs are basically above here, and this whole thing is a 3-dimensional space. So that's how you can visualize the segregation between cats and dogs. So the features are still in effect. We still need features, and we have multiple features now. So we have to make sure that what kind of feature offers us the best segregation. And our perspective has changed because now it's not 2D anymore, it's 3 dimensions. And the thing with ML problems and ML models is that you can never run out of features. You would always have tons of features to work with. So that's like the game, and that's like the game that you need to master. So you'd be thrown in with like tables with 100 columns, and your client would tell you to find some prediction out of it. So as stated here, like most ML models have even higher dimensionality, like 20D. In this case, this is like 3D, but 20D, or even millions in case of image recognition and some video-based models. So yeah, let's talk about a bit about dimensionality, something that we touched upon here. So at the start of the video, I told you that we were given some features. Let's say your intern chooses to segregate between your cat and dog model in terms of the number of whiskers. Now, that's not a very good measure because there are no standard number associated with with dogs or cats in terms of the number of whiskers. Like it's pretty it's pretty general and not pretty specific. So when you're in one dimension, when you choose one dimension, so you can see how hard it is to split. Again, we're back to this particular problem where we couldn't even find the pattern. The same is here because our feature is very bad. The choice of the feature is very bad. Then our manager tells your intern that, hey, this is not working out. You need to spread the data out. For that, just use another feature. Just figure something out. And he chooses another feature, which is like the spots on the body. Or, yeah. Again, that's not a very good feature because, again, no particular number or generalized term is associated with dogs or cats. They can have as many spots as they want. So again, now you're in a in a bit of a pickle as well because you now cannot build a pattern here. So your manager tells you that, hey, okay, just add in another dimension. So now your intern actually adds a very useful dimension, which is like the length of the ears. So obviously cats have smaller ears, but most of the dogs can have small ears, can have large ears, so probably larger than cats. So now things have started to appear a bit interesting. Now again, we're back to this dimensionality setup where cats are scattered over here and we have dogs here and we have this particular plane that sort of does the job for us. So sometimes adding more dimensions can solve a particular problem in terms of data, but that's not something set in the stone. A lot of data can deviate your ML model into wrong directions as well. So that's the actual game is in terms of the data, in terms of mastering the story that your data is telling. All right, let's talk about data hunting. So some beginners would be like, okay, that's cool. I want to build a classification model between a cat and a dog, and I'll start with 100 images. That's fine. That's not right. That's absolutely crazy because imagine, just like stated over here, that to build a decent model you need at least like 10,000 20,000 images within the start to actually start with your decent machine learning model. So that's the thing, and sometimes data is hard to find, but luckily we have websites like Kaggle, which provides you with some great open source data collection, so you can go ahead and use it at first. So an ML system cannot predict stuff if it does not know about it. Yes, that's correct. So let's say we actually built a model and we only provided data or features about a particular dog and a cat. Now, and let's say these are the features that are listed within this slide. Is like number of legs, color, weight, animal. So in case, let's say we provided a few about a dog and a chicken. Now, if you come up and provide one feature which relates to a cow, like it has 4 legs, it's black and 200 kg. So obviously it won't be a chicken. Our model would just say that it's a dog because it was never trained over a data that exceeds 10 kg or 12 kg, 15 kg. So you need to make sure that whatever data you provide is relevant with the kind of entities you want to recognize or entities you want to predict. So let's skip this video. Okay, how ML systems are trained, learning style. So the very first and popular one is supervised learning. So what supervised learning basically means is like it's a supervision. It's a supervision in terms of data that you're like, hey, I'm going to provide you you're talking to your model, and you're just saying that I'm giving you this data and you just need to learn the patterns. You are in control because you're providing all kind of data. So in this particular example, you would let's say you want to build that model that segregates between oranges and apples. And let's say you provided with this data, you're saying if it's red, if it's 200 gram, it's an apple. If it's orange, if it's 300 gram, it's an orange. If it's green, if it's 150 grams, it's an apple. So obviously you would be providing the series of data to your model, and you're constantly telling in each row that, hey, if this is the color, this is the weight, this is the label. By the label, I mean the sort of classification that you want to achieve. So you're constantly telling your model in each row that what are the features and what is the end result. So every single time when your model is trained, it would know from the data that you provided that, okay, if these are the feature set, then this is the closest guess that I can give. So that's a bit about supervised learning. Unsupervised learning, as the name suggests, now you're not supervising. Now a data is given that has no patterns. For example, you need to find a tumor within the x-ray of a brain. Your model won't know where to start from, but it has to start from somewhere. And it has to make a few observations, and it has to collect a few data points and build its own stuff around it. So that's what unsupervised learning basically is, and it has quite a lot of interesting categories and applications as well. So it's just about starting from somewhere, building patterns, and then sort of giving some sort of a guess or an end result that, hey, I think this is the tumor. So that's what being discussed over here. Then we have another branch which is called reinforcement learning. Now, reinforcement learning is heavily used in robotics. So it's like a learning from trial and error. It's like you're parenting your toddler. Whenever he does something right, you actually reward him, and whenever he makes a mistake, you actually sort of not actually punish him, but sort of punish him by not giving him the reward. So your kid actually starts to learn that, hey, if I do these things, I can collect more candies. And if I do these things in a series or in a row, then I can get more sweets or more chocolate or whatever. So that's exactly the concept over here. All right, the $1,000,000 question. How does it all work? I think everybody wants to know this particular question in today's age. So let's talk about it. And the answer is many, many ways, because there are so many machine learning algorithms out here. All right. So here's a first example. And this is something I stated to you guys. And this is also like the very first hint towards the very first and the most simple form of a machine learning algorithm. So the very first example that I actually stated was, you consider that you have a few data points and your teacher asks you to fit up a line which sort of encompasses or touches most of the data points. So in this case, this is that line. These are data points. Or in this case, this is a straight line and this is a quadratic line. And lines obviously can be simple linear lines, or it can be quadratic or maybe polynomial as well. So this particular problem is known as regression, where you actually predict a future value. Now let's say this data point is about the number of days I woke up, at the time at which I woke up. So let's say this is Monday, I woke up at 8. This is Tuesday, I woke up at 8. And I throw in different data points, and I want to build a pattern or build a ML model that predicts whether I'll wake up at 8 a.m. on a particular Monday or Tuesday, something like that. You guys get the idea. So let's say I want to build something like that. So in order to do that, I have to throw in my data points. I make sure that I sort of draw a straight line across it. Most of my data points are covered. Now, whenever I throw a particular point over here, I would just read in the value, and that value is my actual answer. And the same for this case. These lines can be quadratic, as I stated above. So this form of basically applications are called regression. If you have a straight line, it's called linear regression. If your lines are quadratic, then they're called polynomial regression. There's also a multinomial regression as well. So the idea of regression is just to predict a future value over a given data. And the numbers, the example number 2 is about clusters. Now, this is something that we discussed. So here, in this example, we use a line to divide the 2 clusters. So this is like one data point about a specific entity. This is like a second data point about a specific entity. As you can see, there may be a few outliers. So this seems like an outlier, which is again something, it's a useful vocabulary within the machine learning world, where outlier just means something that belongs to some. It's like when you have those guys who are freakishly tall, and then your guys are like 5'8", 5'10". You're like, hey, you guys are normal dudes. That guy over here, he shouldn't be that tall. So basically, that's like an outlier. So here, what this depicts is like, this is more like a classification algorithm where you draw a line, determine a pattern where you can find that sweet spot. You can say, okay, if the value is lesser than this particular value, then it's like the apple and oranges again, the example that we discussed in the start of the video. Again, this is again an example of classifications, and one of the common algorithms used here is called k-nearest neighbors. So what happens is, like, let's say you have this data. Just imagine you have this data, and I give you a data point which sort of is somewhere over here, and I ask you that, tell me, where does this lie, or which particular label or entity is this associated with? Is it in the red zone or is it in the blue zone? That's like the simple question that I'm asking here. So what would you do is you would actually calculate the distance between all of these points, the red ones, the blue ones, and you'll make sure you'll compute that which points or which distances are the lowest. So in this particular case, obviously, if your point is somewhere here, it's more closer to these particular points. So k-nearest neighbors evaluates all the distances between different neighbors, and it computes k, which can be 1, which can be 2, which can be 3. It's more like a parameter that is your choice. You get to choose like what the value of k is, and you would see that if you have particular distances, and if k distances tell you that, hey, it's in blue zone, then voila, that's your answer. All right, so neural networks, we're gonna skip this. We'll cover this into deep learning in our probably the very next video. All right, so we talked a bit about some of the output types or some of the algorithms used in machine learning. The very first one is regression, where you would predict a numerical value, for example, price of the house. You can sort of visualize that graph that we just saw, in terms of housing prices. And if you have a straight line, you can say, okay, what's the price of a house in this particular zone, and you'll get a value out of it from the y-axis. Then we have classification, we have clustering that we discussed in unsupervised learning, where you don't have the data. And a common example is related products on Amazon. So that's again a very awesome use case. Like if you're wondering, like, how does it happen that it just shows me the products that I may buy or products that sort of interest me. So obviously that's more aligned with your search history. And then we have sequence prediction, something that has been evolved into the ChatGPTs, the Llama 3s that we have these days. So let's talk a bit more about it. So this is what regression basically is. And this is, again, linear regression, where we have a lot of data points and we are adjusting our lines to sort of find that best fit. The best fit that gives us uh, the least amount of errors, and it sort of encapsulates or covers the most data points. And then we have classification, and where we want to make sure that, hey, if you're given this picture, then what it is it a cat or a dog? And obviously classifications can be done with k nearest neighbor, something that we just discussed, that if you have a data point, you just find distances with each data point. And it can be done with neural networks as depicted in this picture, where you have certain layers of a deep neural network, and you sort of find it within the output layer. But we'll discuss more about it when we actually study deep learning itself and how we can use it for regression or classification. Then we have probability estimations. In this particular example, it's like how much of an occurrence of a particular event is probable. So I know a lot of people, probability scares a lot of people, and a lot of people scream whenever they hear the word probability. But unfortunately, probability is a huge part of machine learning and natural language processing. But it's kind of easy in terms of when you think of it in terms of the application and not in terms of formulas. So for example, in this case, we have an ML system that is used to predict how many white bricks are in the jar on the right. If it outputs 9 with the probability of 54.3, then we can then choose to do something useful. So a common use case or a common model or an algorithm is obviously something called Bayesian algorithms that are basically built upon Bayesian theorems that of conditional probability, that if event A has occurred, then what is the probability that event B is occurring. So obviously we can use this as a stepping stone of triggering another event, or to gaining insight about data that what is the probability that I have woken up at 8 a.m. on a Monday morning. So if I have those probabilities, then I can make my model tell me that how much probable is it that I'll wake up at 8 a.m. on a particular Monday. So if it says like 42%, then obviously the chances are bad. All right. So this is again one of the application that it states that, let's say you build a sort of a machine which has a camera, and let's say your cat sort of comes in front of the camera, and your camera sort of recognizes that, hey, it's your cat. Then it sort of opens up a tray of food for you. It's like a cool product that can be used. So again, the definition is like, if we are 80% sure that what we see is a cat, then maybe we want to feed it. If we are 75% sure, maybe we will wait until we are more sure. So obviously you can play around with your models like that. So type of ML algorithms, how they really work for the curious. So now this section is kind of interesting, and it's stacked with a bit of detail, so you might have to fasten up your seatbelts. So we have already talked about regression, and I think it's pretty... I think you guys will be pretty convenient in understanding that what regression basically is. So regression is concerned with iteratively modeling the relationship between variables using a measure of error in the prediction made by the model. Now just imagine you have a lot of data points. Now how do you make sure that you find the best fit data point? Just imagine you have like 100 data points. Now figuring out the permutations or combinations of those data points is going to be insane. You cannot just make sure that, hey, I'm going to draw every data point just like that. crazy. It's going to take you a hell lot of time. So you have to find a way in which you sort of find the best solution. So what you can do, you're provided with the data with certain features and the label itself. Remember, the label is actually the output that you need. That, hey, it's a cat. Cat is a label. Hey, it's a dog. Dog is a label. Hey, it's an apple. Apple is a label. Hey, these are oranges. Oranges are a label. So, okay, now now that we have in check, so what you would do, you would just throw in, you'll actually choose a particular line, and if you haven't forgotten the formula for a straight line, it's y is equal to mx plus c. So here you have to make sure that what kind of m, which is the slope, and what kind of c, which is like a constant, you would choose from your data. And you'll sort of try different data points, and you will see that if you get the right answer for all of those or most of those data points, all of those data points are obviously is a long shot, but most of those data points, and if you get most of those data points right, most of those labels right, if you get most of the answers of your cats and dogs, apples and oranges right, then it means you're on the right track. And that's how regression works. So obviously, it might make a lot of errors, but readjusting the line while they're making those errors is the process of linear regression. Then we also discussed instant-based algorithm, which is also called k-nearest neighbor. Um, Again, you have a point here. You will check the distance with different neighbors, and you will compute the lowest distance, and the lowest distance is basically your answer. So we've already discussed this in detail. Let's go ahead. Decision trees. So you would see a lot of talking agents or assistants these days, which actually hear what you say and they respond to you accordingly. So that is basically about decision trees. So you have a lot of use cases. Consider it as binary tree, and your model has to choose the best possible way out of that tree. So the common application is conditional decision trees used in dialog flows within these agents that are being used today. And then we have Bayesian, something again we discussed. Knife-based classifier is like one of the applications where you make sure of the probabilities of a particular event occurring, and you make sure that how probable that event is, like me waking up on a Monday. If you can sort of revisit that example. Then we have clustering algorithms. The common ones is k-means or k-medians. This is again, you start from some sort of a distance algorithm first. You make sure that if a particular point or if a particular point or data point sort of helps you build a kind of a region or a cluster. So that's the common case here. So clustering methods are typically organized by modeling approaches such as centroid-based or hierarchical. All methods are concerned with using inherent structures and maximum commonality to sort of categorize data points. Association rules are more like, I don't think you would use it. You might use it within financial applications, but again, if you have some idea about linear algebra or discrete mathematics, then you know that if some events help C occur and C helps D occur, then you can sort of have some sort of, you can associate a few things with these series of events like transitivity or association in general. Then we have artificial neural networks. So the best definition obviously is that it sort of mimics a human brain. So we'll learn more about it when we actually dig into machine learning. So it helps you with regression algorithms. It helps you with classification algorithms. So it's kind of cool. And it's probably the most used and most used method of sort of deriving predictions and classifications. Even in today's world, all the chat GPTs are using it. The RNNs, the convolution, deep neural networks, and stuff like that. So yeah, I think I'll stop here. And after this particular video, we'll be doing another video for deep learning, so you can get a bit of a high-level aerial view of what deep learning actually is. So yeah, this is a bit about machine learning, and in machine learning there are a lot of different algorithms, but if you start with a few ones, if you understand a few ones, it's sort of easier for you guys to pick up on other algorithms. It's not really recommended that you study all of those algorithms, but you should know the concept or the idea or the thought process of what that algorithm actually delivers. So yeah, thank you for watching this video. I hope you learned something, and if you have any questions, you can drop them in the comment section, and I'll see you in the next video.